Thank you, Marta. So, without further ado, I will introduce uh, Dr. Andrew Pawlikowski. Dr. Andrew Pawlikowski is a development and process engineering manager at Johnson Matthey. He received his Bachelor of Science in Chemistry from the University of Pittsburgh in 2000, before going on to obtain his PhD from the University of Washington in 2006. I was a part of the research group of Karen Goldberg, where he was studying the mechanism of novel carbon-nitrogen bond-forming reactions from platinum-4 complexes. Following his PhD, Dr. Pawlikowski did his postdoctoral research at Iowa State University, working in the research group of Aaron Sato, doing organometallic rare earth chemistry. He returned to Pennsylvania after to become an adjunct professor at Arcadia University and Delaware County Community College in the greater Philadelphia area, teaching general chemistry to undergraduates. He was hired by Johnson Matthey in 2011 as a product development chemist in the refining and chemicals plant in West Deptford, New Jersey, and was promoted to development and process engineering manager in 2017. Where he now supervises a team of chemists and chemical engineers who do a number of operations support activities, including process troubleshooting and optimization, as well as new product development and scale-up, which brings him to talk to us today. Dr. Pawlikowski was born outside of Chicago, but grew up primarily in Lancaster, Pennsylvania. He is married with 2 kids, aged 10 and 5, and he enjoys craft beer, camping, and darts in his free time. So without further ado, Dr. Pawlikowski, really excited to have you here today.
All right, thank you. Thanks for the great introduction. And I also want to say thank you to the center for extending me the invitation to speak. I'm excited to tell you about the company I work for and all the exciting things we do related to PGM chemistry and a lot of other things. So I think if that's okay, I'm going to try to stop my video and just go full screen on the slides, and then I can come back at the end if that's all right with everybody. Okay, let me know if you can see that.
Yeah, we can see that. You also just show up as a black box. So if you'd like to just put your video on, that's also fine, because it doesn't really matter either way, because it doesn't full screen, at least on the recording. So just as a heads up.
Okay, thanks. All right, so I'm going to talk to you today about Johnson Matthey. I'm going to give you a little bit of a history of the company. We've been around for a long time, tell you a little bit about global operations, kind of our current structure and our strategy, hopefully relate that heavily to sustainability. And then I'll take a little deeper dive into my plant in West Deptford, New Jersey, which is fairly close to UPenn, so we're neighbors. And I'll tell you a little bit, in more specific detail about what happens in the West Deptford refining and chemicals facility. So let me start by is this working? Okay. So I'm just going to start with the company vision, because that pretty much sums up our goal here. So the vision of the company, our vision is for a world that's cleaner and healthier today and for future generations. So we're a global leader in sustainable technologies, and we apply our science to catalyze the net zero transition for our customers. By applying our inspiring science, we enhance life for millions of people all across the world every single day. Lead with can you guys hear this? Could you guys hear that video? Is it coming through the audio?
I cannot hear you.
Correct. I cannot hear it either.
Okay, I'm just gonna play. This is a video from our CEO. I think it has subtitles here, so I'm just gonna go for it and just play the video. If you really can't hear or see, then I'll just cut it.
I was gonna say, if you want to go back and try resharing, and then usually there's a box at the bottom that says optimize video quality, then that usually makes the video come through. It's one of those tiny boxes that everybody forgets about, but makes a difference.
Okay, so I stop sharing and then...
Yep, stop sharing and then try sharing again. And when you get that box that asks you which window to share, At the very bottom, there's like a little box that says like optimize video sharing or quality or audio quality, something like that. Do you see that?
Yes, share sound and optimize the
Yeah,
video.
yeah. Click those boxes and then try again.
Ooh, okay. Let's see. Okay, can you see it again?
It's working on it. It's thinking real hard. It says it started screen sharing. I can hear it. I just can't see it right now.
Okay, I'll pause and then see if it comes up again.
It's funny. It just says has started screen sharing.
All right. How about, do you see this slide or no?
I see nothing other than has started screen sharing.
Interesting. It tells me I am screen sharing, so.
You're welcome to unshare and share again if that helps. It may be like the window you selected in terms of what it is that you're sharing.
Okay, let's try again.
Like if you specify the PowerPoint window and also make sure those boxes are checked. Anything?
Yeah, I just tried that again.
Is anybody else seeing anything other than his name and black screen? It might be too much for his Wi-Fi. That's possible.
I'm seeing a girl sitting by a plain window.
Okay, that's good. That's a slide. Nobody else sees that?
Oh, interesting. So you can see that.
Mm-hmm.
That's interesting.
All
I just
right.
see a black screen just saying that you started screen sharing.
All right, let me try
Well,
one
this
more
is
thing.
bizarre.
Let me, and if I have to skip the video, that's fine too. Let me just click the share sound one and see if that helps in any way.
Oh, I see a screen. I see slide.
All right, so let's try to advance here, and then again, I'll just, just let me know.
Yeah. Oh, I can hear it too. Yay!
All right, success.
For over 200 years, Johnson Matthey has focused on turning the magic of precious metals into scientific progress that can help address some of the biggest societal, economic, and environmental challenges that exist. Right now, that work is more critical than ever. The world is facing a momentous challenge that will determine the fate of everybody on our planet. How to combat the threat of climate change so that we can all live within our planet's boundaries. Since joining as CEO in March 22, I've been really impressed by how deeply passionate everybody is to meet this challenge head on. I've been equally impressed with how important JM is for our customers, who are literally dependent on us delivering for them to meet their business and sustainability commitments as well. It's not unusual for us to have worked for decades with our customers, sometimes even spanning generations, which is testimony to the quality of our science and the trust our customers put in us. 50 years ago, it was our pioneering technology that created the world's first commercial catalytic converters, which have enabled billions of people to not have to fear for their health due to harmful emissions. Our automotive customers are being asked to meet the strongest ever clean air health requirements. And as they transition to net zero emission vehicles, we're supporting them again, producing critical components for hydrogen fuel cells, the most sustainable way available to ensure clean transport for larger vehicles. Our chemical industry customers are responsible for so many of the building blocks that go into everyday essential household products. We're supporting their decarbonization ambition to turn their factories and production processes green as they seek to shift to more sustainable materials and products to make everything from sustainable paints and plastics to decarbonized fertilizers. And while coal, oil, and gas have dominated the energy industry for generations, our energy customers are now looking to us for help in leaving those fossil fuels behind. because we're experts in the process technology and catalysts needed for a wide range of sustainable fuels, from blue and green hydrogen to sustainable aviation fuel, methanol and ammonia. Johnson Matthey is at the heart of the energy transition, just as it is at the heart of the chemical and automotive transitions. All of our customers are facing the same transformation challenge, the need to develop more sustainable products at unprecedented speed. We have a bright and green future, and the world is depending on us to deliver for this and for future generations.
Okay. So yeah, if you want to hear more about our strategy, I'll tell you a little bit more about it, but there's some website information. That was Liam Condon. He's the new CEO who joined in March. Thought it was a nice video to kick things off. So Johnson Matthey was founded in 1817. So actually this week, we hit our 205th anniversary. We had cupcakes in the plant to celebrate yesterday, which was exciting. So over the last 205 years, we've built a brand and a reputation. And throughout this time, we've innovated and brought new products and technologies to market, adapting to the changing world and the changing needs of our customers. So we have leading positions in a number of the markets that we serve. You can see some of the profitability numbers there. And it all comes from our world-class science and technology and how we apply that to help solve customer problems. So looking at the number of employees, we're I would say a small to medium size global company, still based in the United Kingdom, but operations in, I think, 30 plus countries worldwide. So let's talk about those 200 years very quick. I'll just give you a couple of the highlights. So 1817, Johnson Matthey set up Percival Norton Johnson set up a gold assaying business in London. So that's from the very beginning, we've had a hand in precious metals. And throughout the 1800s, it was all about pioneering metallurgical science. So 1861, JM was appointed official assayers to the Bank of England and official refiners. Later on, they actually produced a standard kilogram and a standard meter made out of a platinum iridium alloy, very corrosion resistant. Then into the 1900s, really they started to establish their PGM, platinum group metal, expertise, and started to kick off a lot of research and development activities as well. So in 1926, JM developed and patented the first method for the extraction of platinum. So this was kicked off by the discovery of vast PGM deposits in primarily South Africa. So they found these PGM deposits, PGM ores and minerals. They contain different combinations of elements and base metals. So in order to be able to process and get the value out of this, they needed new technology, new chemistry. So Johnson Matthey R&D got involved and really came up with the first process to be able to do this. So that really kicked off the PGM refining efforts to refine these metals from ores. Prior to that, a lot of the PGMs were from more alluvial deposits, so kind of natural deposits of platinum and platinum alloys, similar to how you find gold, out in creeks and things in the West. So also in the 1900s, Johnson Matthey established a US presence. So they actually partnered with a company called Bishop and Company. It was actually outside of Philadelphia, so that's why we're here now, I suppose. So they started establishing refining capabilities over in the States. In the 1960s, got involved in the space program and actually contributed to some fuel cell technology to power equipment on the first Apollo missions. So that was pretty neat. Then in the 70s to the 2000s, again, furthering our expertise in PGM chemistry and catalytic applications. So 1970, low pressure oxo process was developed with Dow for producing oxo alcohols. So typically those use rhodium-based catalysts like Wilkinson's catalyst and derivatives. 1974 was a milestone. JM actually made the first components for catalytic converters. So from the very beginning, we've been in the emission control game, enabling car companies to meet new legislation. 1983 got involved in some health-related applications for PGM. So JM commercialized the first platinum-based anti-cancer drugs. So that actually, at the time, spawned a new division of Johnson Matthey, manufacturing active pharmaceutical ingredients. We recently, just this year, divested that part of the business, so we're no longer involved in pharmaceuticals. But all of that started because of these platinum-based anti-cancer drugs, some of which used to be manufactured at West Deptford, where I'm at now. And then in the 2000s, kind of shifting focus to science and sustainability. 2007 launched Sustainability 2017, a vision for building a sustainable business. 2017, so 5 years ago now, we rebranded ourselves as a sustainable technology organization. 2021 launched new ambitious sustainability and net zero goals, and just this year launching a new strategy after the new CEO who you just heard came aboard, all about catalyzing the net zero transition for our customers. So let's talk about that strategy a little bit. So the strategy is focused now on catalyzing the net zero transition. So we're making it our business to help address 4 essential transitions the world needs for a sustainable future. So transport, chemicals, energy, and creating a circular economy. So driving down transport emissions, transforming our energy emissions to get away from fossil fuels, decarbonizing chemical production, and then the circular economy relates to recycling of PGMs. So keeping these very valuable rare elements in circulation. So this is the strategy of the business now. So I'll go over in a little bit more detail of each of these. Climate change and increasingly stringent air quality regulations are pushing the automotive industry to build cleaner engines and use new fuel sources. And our technologies are helping our customers in the automotive industry go through that transition. Today, our emission control systems or catalytic converters are used in cars, buses, and trucks around the world, every year helping to remove 20 million tons of harmful pollutants like nitrogen oxides and particulates produced by gasoline and diesel engines. Despite a growing number of government deadlines to phase out gasoline and diesel vehicles, the transition's not going to happen overnight to get away from the internal combustion engine. So we continue to innovate and improve these technologies to meet new emissions legislation and keep people moving in the cleanest way possible while the transition towards batteries and fuel cell vehicles takes place. So on the alternative fuel side, we're also heavily involved in supplying crucial components at the heart of hydrogen fuel cells, for hydrogen-powered vehicles. So these catalyst-coated membranes and membrane electrode assemblies are becoming increasingly used in commercial vehicles, such as trucks and buses. Transforming our energy systems. So if the transport transition is all about moving people and goods while lowering emissions, the energy transition is about finding sustainable ways to power our world. So hydrogen, again, has a huge role to play here. You hear a lot about blue hydrogen, green hydrogen.
Still there?
Yes, can you hear me? Hello?
Uh-oh.
Hello?
Okay.
Can you hear me? Yes?
No? Now I can. I can't tell if it's just me or if it's
I could
or
hear
if it's on your
him
end.
most of the entire time.
Oh, okay. All right. I have no idea. I'm literally at the university, so I have no idea why it just cut out. So, all right,
just
continue. Sorry.
Please chime in if that happens. I don't want to just be talking here into
Yeah,
space,
yeah. No,
but
okay, perfect. All
I
right, thank you.
appreciate that. Yeah, so clean hydrogen production technology. When hydrogen's burned as a fuel, the only byproduct is water. So we want to make sure we can produce hydrogen with a low carbon footprint. And so we have LCH technology to enable low carbon hydrogen production from natural gas while capturing CO2. So that technology is being commercialized at scale in the UK. And then in the electrolytic or green hydrogen space, we're building on our experience in fuel cells and using our expertise to develop and manufacture components for electrolyzers, which use electricity to split water to hydrogen and oxygen with zero carbon emissions. Our technology is also enabling the production of sustainable fuels. Sustainable aviation fuel, and sustainable methanol and ammonia technology. I'm not going to talk too much about those because I don't really know a lot about those areas. Decarbonizing chemicals production. So the world relies on chemicals. They are in everything from our clothes to cleaning products, food packaging, medicine, but the industry, like transport and energy, the industry was built on fossil fuels, so that needs to change if society is to reach its net zero goals. So our catalyst and process technologies businesses are helping our customers in the chemical industry decarbonize their processes and use more sustainable feedstocks. So syngas is a big player here. So our technologies are helping to reduce the carbon footprint of traditional production of syngas and enable the production of syngas from sustainable feedstocks like biomass. Using JM technology, our customers transform syngas into chemicals such as methanol for paints, formaldehyde for construction materials, and ammonia for fertilizers. So as the industry transitions to net zero, more and more chemicals and fuels will be produced from sustainable syngas, and JM technology will be at the heart of that transition. Creating a circular economy. We helped create one of the world's first circular economies in platinum group metals, PGMs, so critical components of everything that we've just described. So this is where my part of the business fits in. We are the #1 recycler, secondary recycler of platinum group metals in the world as a company. When I say secondary recycler, so primary refining refers to the mining operations. So if you're extracting PGMs from the ground and refining them into elemental form, that's primary refining. Secondary refining is the recycling. So PGMs that were already out on the market, bringing them back in and turning them back around into useful forms. So right now, about 70% of the PGM used in our products comes from secondary supplies. So this is just super critical because these are rare, expensive elements. So the more we can keep these in circulation, the better off we'll all be. And then reducing the carbon footprint of our products and our customers' products. A lot of the technologies I've already gone over. So then you hope that the tech companies that are using our technologies and our products, can then have a process to recover their scrap or waste and then get it back into the market, get it back to us to get more value out of it. So all of that converts into just this the current Johnson Matthey organization structure. So we have 4 core businesses focused on meeting customer needs to catalyze this net zero transition in our 3 key markets, which are automotive, chemicals, and energy. So Clean Air is a global leader in auto catalysts that remove harmful pollutants from gasoline and diesel vehicles. Catalyst Technologies supplies catalyst and process technologies to enable the decarbonization of the chemical and industries. And then hydrogen technologies provides critical components for both those green hydrogen electrolyzers and the fuel cells technology. And then underpinning all of that, you have Platinum Group Metal Services. So this Platinum Group Metal Services, or PGMS, is again a leading recycler and refiner of precious metals. So we have a couple of value businesses that I won't go into at all, but kind of on the side. And all of this is enabled by, corporate functions, enabling functions, supply chain, EHS, process safety, legal, and then a huge corporate R&D function as well, and enabling a lot of this amazing science. So the structure is, designed to capitalize on the strong synergies across all of those areas. So you have the core businesses focused on the 3 key markets. There's a lot of mutual customers and partners and shared technology. But where I fit in here is really on the foundational PGM ecosystem. So PGM services, or PGMS, we're feeding the businesses with the metal, with the products, with the catalysts that they need to do their science. Yeah, so just overall as a company, we have an unrivaled expertise in PGM chemistry, catalysis, process optimization. So a lot of opportunities for, young chemists, young engineers to get involved. Our heritage from the beginning, from the history that I outlined, is in the precious metal refining. So, we know a lot how these metals behave, how to harness catalytic properties, how to recover and recycle them. Full experts, across the full spectrum of catalysts, heterogeneous, homogeneous, biocatalysts, correlating structure to performance, things like that. Process engineers make sure that everything is as efficient as it can be, as safe as it can be, trying to keep costs down. So all of these areas, really support our operations. And then we have a corporate research and development team that provides the backbone of the core science capabilities. So this is it's a site over in the UK called Sonning. It's a team of over 1,300 R&D scientists developing cutting-edge innovations to try to support all of these businesses and meet our customers' challenges. So I visited there once. It's a pretty amazing place. It's on this old estate in the English countryside, and it's just this little utopia of scientists walking around, all kinds of instrumental capabilities, advanced characterization techniques, etc. But so they are sort of they're doing the core science, trying to find new applications for things, and then also helping the various business units innovate as well. So coming back to sustainability a little bit, I've talked about how the company as a whole is approaching sustainability with customers, but we also have our own sustainability targets for ourselves. So our sustainability goals, came from the United Nations Sustainable Development Goals, and really there's 3 buckets they fall into. So products and services, operations, and people. So for products and services, that's a lot of what I've already talked about. So making sure that our products will have the greatest impact in accelerating progress toward this net zero transition. And we also measure our impact on driving lower global greenhouse emissions, less air pollution, et cetera, and our conserving resources by recycling PGMs. Operations, we're aiming to reach net zero in our own operations by 2040 with targets for our internal greenhouse gas emissions. And then people, we're committed to a safe and inclusive internal culture, ensuring high ethical standards in our value chain and supporting our communities. So we need the right people in our company and value chain to achieve these ambitions, and we want to keep everybody safe, happy, and respected. This slide has a couple of recent highlights just related to sustainability. not sure how much I'll go into these, but AAA rating from MSCI, which puts us, it's the highest possible rating, puts us above our specialty chemicals industry peers. Retained membership in the Dow Jones Sustainability Index in Europe places us in the top 6 European chemical companies and 92nd percentile globally. So lots of high scoring things and accolades. There's a couple of bullet points related to the sustainable fuels. So first aircraft flight powered by 100% sustainable aviation fuel was powered by a joint venture between JM and a company called Virent. Sustainable fuels production, and some of our technology is also being used in the world's first climate neutral methanol plant. So that will produce sustainable methanol from green hydrogen and carbon dioxide captured directly from the air. So that's a new project in Chile, I believe, in South America. And then some bullet points about milestones with fuel cells vehicles. We're working with a lot of companies now on green hydrogen electrolyzer technology, yeah. So that kind of ends my corporate spiel, I guess, about the company as a whole. So now I'd like to talk a little bit more about what I do and how we fit into this picture. So I sit in the business called Platinum Group Metal Services. So this is related again to that foundational PGM ecosystem that I talked about. So there's really 2 parts of this business. Precious metals management is the trading part of it. So they buy and sell precious metals. They monitor the prices, buy and sell, market research, et cetera, et cetera. So they're the distributor of the PGMs for the business. And then on the other side, you have PGM refining and chemicals. So refining and chemicals, we're doing primary and secondary refining of PGMs to recycle these valuable elements back into the market. We manufacture a wide variety of PGM chemicals for a whole slew of various industrial applications. So the refining business supplies the metal for the chemicals business, and then we hope that at end of life, the metals find their way back in to complete the cycle. So I had this slide in here. I saw that you had somebody else talking about PGMs and precious metals, but I just wanted to make the distinction of what do we mean when we say platinum group metals. So there's 6 of them right in the middle of the periodic table: ruthenium, rhodium, palladium, osmium, iridium, and platinum. As far as Johnson Matthey goes, really we hit 5 out of the 6. So we really don't deal with any osmium. So that's the odd man out there. When you talk about precious metals then is the platinum group metals plus gold and silver. In the pictures there, you see some vials with metals. The palladium, silver, platinum, and gold look shiny and metallic. So that's metal in grain form. The ruthenium, rhodium, osmium, and iridium are more powdered, just looks like a gray powder. So that's a form which we call sponge. Commercial grade PGM sponge is just metal powder instead of metal grain. In the industry, we talk a lot about base metals also. So base metals are pretty much anything else that we don't necessarily care about as much as the PGMs. Common base metals that we see are things like iron, nickel, copper, a little bit of chrome. And then, there's some other valuable semi-precious metals that are used for a number of industrial applications: rhenium, tungsten, molybdenum, etc. And then common battery metals would be things like cobalt, nickel, copper, and lithium. So some of those base metals are used in battery technologies. So just wanted to clarify, since I keep saying PGM and precious metals, just to clarify that. So I think another one of your presenters had a similar slide from Johnson Matthey, actually, I noticed. But this is just a price chart. I just pulled numbers for the last year. just show you how the prices fluctuate. For the last several years, rhodium has really been dominating the market in terms of price. So you can see for the last year, the average rhodium price was $16,000 a troy ounce. A troy ounce is the unit of measure that we deal with in the precious metal industry. 1 troy ounce is approximately 31.1 grams. So not a lot of material. 31 grams of rhodium. You know, you can see around February of this month was about $30,000 for 31 grams of rhodium. Platinum has remained mostly stable, even through my 11-year career at JM, always right around $1,000 an ounce. Palladium about double that now, but they do fluctuate year to year. So again, just making the point that these are very expensive, valuable metals. And then you can kind of think about, use these numbers to put into context, like the amount of PGM and the value that flows through our facility in the next couple slides when I go over that. So refining and chemicals. I'm based in West Deptford, New Jersey. We have refining capabilities in the UK and also in China. So Shanghai in China is a chemicals plant. Zhangjiagang is a refinery. In the UK, we have Brimsdown and Royston. Brimsdown is a unique site. It's the oldest site. I think one of the pictures on my history slides from 1926 was actually taken at the Brimsdown site, and that site is still in operation today. But they have smelting operations, which allows them to upgrade low concentration PGM feeds, allows them to concentrate the PGMs up, and then they send that concentrated feed over to the refinery in Royston for further refining and processing. And then Royston also, it's the corporate headquarters, and they have chemicals plant there, and then they support a number of the other businesses as well. And then West Deptford, New Jersey, we are refining and chemicals, but we are only a 3-metal refinery. So we deal only with platinum, palladium, and rhodium, whereas Royston does 5 out of the 6 PGMs. They also refine ruthenium and iridium, but we do not have those capabilities in West Deptford. So where is West Deptford? It's right across the river from the Philadelphia International Airport. So right up there under where it says Philadelphia Museum of Art is probably right around where University of Pennsylvania is there. So not too far away. Johnson Matthey has other facilities in the Delaware Valley. We have clean air plants that are up near King of Prussia in Pennsylvania. We have a PGMS facility in West Whiteland, which is near Westchester, Pennsylvania. They deal more with just the metals themselves. So processing PGM and alloys into tubes, wires, sheets. They have a giant loom over there that weaves thin platinum wires into gauze. So they are the metal handlers over there, and then we are in the chemical side of the business across the river. So how does all of this work? So this is a oversimplified process flow of, and I'll try to track the metal through. So let's start in the gray box that says customer byproducts and recyclables. So customers, because we're a recycling facility, customers supply the metal that we work with. So we have customers that send in mining concentrates, recycled PGMs in a number of different forms. So from catalytic converters, spent catalysts, etc. We don't receive the actual catalytic converters. There are companies out there that collect catalytic converters, put them through smelting operations to upgrade the PGMs, and they produce a PGM concentrate that then comes to us for final refining. You know, spent pharmaceutical catalysts, palladium on carbon, filter media, gauzes, you name it, anything in the industry. Dental materials we used to handle back in the day. A lot of dental alloys contain palladium, gold, silver. And then we get some metallic scrap as well. So industrial scrap or jewelry scrap. some of it is internal from the facility in West Whiteland that I mentioned. So our target, we're a pretty high grade facility, so we're targeting maybe 10% PGM content or above, and we will take that material and process it. So the first step in the whole operation, since it's customer metal and it's valuable, the customer wants to get paid for their value. So the first thing we have to do is homogenize the material and pull a sample and assay that sample to tell them exactly the price PGM content in the material that they've shipped in. So this sampling and assay process we call evaluation. So that's step one before we can process. So as far as evaluation goes, the first thing we have to do is get it in a form that can be sampled. So if there are burnable materials, if there's carbon or anything, organic solutions, anything that can be burned, we're going to put it through an ignition process. So we have large box furnaces and liquid furnaces. You load material into trays, burn it at high temperatures. Carbon and other volatile elements are burned off, leaving behind a metal-rich ash. So this ash then can be ground up, homogenized, screened, and put through powder sampling equipment. If we get aqueous PGM solutions, which is rare, that's a little bit easier. You just have to make sure it's homogeneous and sample it, and then you can put it in some cases directly into the process. Metallic materials are a little bit more difficult, so you can't burn, grind, screen, sample metallics. So we actually melt those. So we have induction melting furnaces. We'll melt the whole job, and when it's molten, we can pull a solution sample of the melt. That will solidify into a pin that gets cut up and sent to the lab for dissolve and assay. But the whole idea here is that you need to get a representative sample. If we make any mistakes in this area, either we are losing a lot of money or the customer can lose a lot of money. So this is arguably, it's the least, I guess, the least sexy part of the whole operation. If I can say that, it's a lot of manual handling and processing, but arguably the most critical from a business perspective. We could have the best analytical laboratory in the world giving us the most accurate assay, but their assay is only as good as the sample that we provide them. So that, there's a lot of risk and a lot of potential for errors in that process. I guess there's one additional step for metallic materials. After you melt it, you pour it into an ingot. These ingots are just too big and heavy to dissolve efficiently in our refinery. So there's an additional step. We have to convert it to a metallic grain or like a metal sand, some form that we can more easily dissolve in the refinery. And then we're ready to go on the refining side. So going back to the flow chart here then. So we've sampled and assayed the material. There's a commercial settlement that takes place. The customer has to agree with our assay. In many cases, they test their own samples. They have to come to some kind of agreement. So back and forth. Sometimes we have to send samples to a third-party lab as an umpire. But once all of that happens, the metal is credited to the customer. The physical metal then is ours to put into the refining process. And then after this point, we lose all customer traceability. It just goes on a list, and then we just start charging things and dissolving and putting it through the process. So this is where the PGM refining happens. So after we go through our hydrometallurgical refining process, the outputs of the refinery are either commercial grade PGM sponges, so those powders that we saw, 99.95+% purity for platinum and palladium, for example. Or if we're not going all the way to sponge, we will output PGM salts or solutions. In some cases, these are sold directly to customers. In a majority of cases, they are sent down the hall to the chemicals plant to be used as raw materials to manufacture other products. So the way it all works is the chemicals plant has orders, they have products they need to make. The refinery supplies them with the necessary metal to make those products. once we hit those limits, we don't generate a lot of shelf stock. Everything is made to order because of the value of the metals. There's a lot of working capital implications. So once we hit the demand for chemicals, all of the additional PGM goes to sponge. So once it goes to sponge, it can be transferred over to the precious metals management division, and then they take it from there for their buying and selling activities. So let's talk about refining and how that works. All right, so it's a hydrometallurgical process. So we do chemistry in solution. So step one has to be to get PGM feeds dissolved into solution. So I'm sure everyone on the call knows that PGMs are notoriously difficult to dissolve. You need harsh, very oxidizing conditions to be able to put these into solution. We use either chlorine and hydrochloric acid, or in some cases aqua regia, which is a mixture of hydrochloric and nitric acids. We use that primarily for the metallic grain. So everything dissolves into solutions, PGMs and base metals. We can filter off any insolubles. The insoluble residue will get burned, ground, screened, sampled, and then either put back into the process or sent overseas to our smelting facility over in the UK. Anything in solution moves on. And now we start our PGM separation processes. So PGMs are selectively precipitated one at a time from solution as impure PGM salts. And the whole idea is that you only get one metal at a time and the base metals remain in solution. So all of this is based on inorganic redox chemistry. So we exploit the redox chemistry of the elements. We put things where we want them to be. We add selective precipitating reagents and remove the metals one at a time. So for example, you remove platinum first as a salt. You filter that off. Now your solution contains palladium, rhodium, base metals that flows somewhere else. You do a second reaction to then selectively precipitate the rhodium. You filter that off. Your solution now contains the palladium and the base metals. You get the palladium out. And now you're left with a solution that's primarily base metals with a little bit of PGM. So I'm going to skip a box and go all the way to the end for waste treatment. So you have these solutions with base metals and trace PGMs. We have waste treatment processes that are designed to just crash out the residual PGMs from solution and recover them. And then the base metals are knocked out in a wastewater treatment plant through hydrolysis to make base metal hydroxides. Those get filtered off, sent to a refining partner for metal recovery. And then we strip ammonia from the wastewater and then test it. And if it passes specifications, it's discharged to the county wastewater treatment facility, utilities administration. So the step I skipped over, PGM purification. So now we have these crude salts, platinum and palladium and rhodium. So they go to their own areas of the refinery where we do purification steps. We're going to redissolve these and do additional chemistry to reject more impurities and turn them into pure PGM chemicals. And then we will do some kind of a chemical reduction to convert it to a PGM sponge or powder, or outturn it as a clean PGM solution. So that, in a nutshell, is how the refining process works. Just some pictures on the bottom. On the left, that's one of our dissolve reactors. This high-powered agitator to make sure everything is suspended. They sparge that with chlorine. The coil you see is a heating and cooling coil with steam or cooling water. The middle, you have a filter box. So that yellow salt is one of our platinum intermediates, just captured on this filter box. And then to the right of that, it's just platinum sponge. This looks like a gray powder. The chemical you see there is chloroplatinic acid, or CPA solution. When you dissolve platinum sponge, you make hexachloroplatinic acid, or CPA. Okay, the PGM refinery outturns. So just to give you an idea of the scale of operations, you really want to only look at the end of the chart there. This is from 2006 all the way to 2023. But palladium, 160 to 180,000 troy ounces per month is outturned as sponge or chemical product. So for those that don't typically think in troy ounces, that's 5,000 to 5,500 kilograms of palladium, pure palladium, being outturned every month from our facility. Platinum, 60 to 80,000, maybe a little less, 50 to 70. But that's somewhere in the neighborhood of 1,500 to 2,500 kilograms of platinum. Then rhodium, 12,000 ounces a month, or about 375 kilos of rhodium. Okay, so that covers the refining process. And now we are manufacturing chemical products. So the PGM sponges or salts or solutions that we outturn from the refinery can find their way over to the chemicals plant, and they're going to do other inorganic chemistry to convert those raw materials into other value-added products for a number of different customers and a number of different industries. In some cases, we manufacture additional raw materials that then move forward to, for example, to our supported catalyst department. So they're going to use different PGM raw materials to reduce PGMs onto carbon, particulates, fuel cell catalysts, eye care discs, etc. Eye care discs I'll explain in a second. Yeah, so we're just manufacturing other chemicals to feed the industry. It's a 5-metal chemical plant, so we do manufacture some products with iridium and ruthenium, but we source those materials externally, either from our UK refining partner or some other suppliers. So then we sell these chemicals to customers. We hope the customer generates some waste product of some kind with PGM. They can send it back in and start the whole process all over again. So on the chemical product side, PGM products are manufactured in, up to maybe 100 kilo quantities in batch processes. It's a lot of primarily aqueous acid base and redox chemistry. We do manufacture some organometallic products in our what we call our organo room. These products need a different level of control because of the flammable nature of the solvents and the air sensitive nature of the processes and products. This picture here is actually our organo room. You can see 4 reactors in there. There's a 30-gallon on the left, a 200-gallon kind of in the middle, and then 2 100-gallon reactors on the right. So those are glass-lined steel vessels. Typical overhead agitation, heated and cooled with a jacketed system. And then we also manufacture heterogeneous catalysts by reducing PGMs out of solutions on the supports. So this is just, I could talk for hours and days and weeks about our products and applications. I know coming up close on end of time here, but here's just a flavor of some of the products that we make. PGM chloride and nitrate solutions. PGM nitrates, platinum, palladium, and rhodium nitrate, for the most part, go internally to our clean air division. Those are used as precursors for the automotive catalysts. But any of these, they're automotive catalyst precursors, supported catalyst precursors, pharma catalyst precursors, etc. We make some specific solutions that are used for plating, electroplating of platinum primarily. So the aerospace industry uses these baths to plate platinum onto the surface of jet engine turbine blades. They're looking for heat and corrosion resistance. So this platinum Q salt is an ammoniated plating bath that's used in the aerospace industry. PGM powders, I'll talk a little bit more very briefly about some of our what we call PGM blacks, which are like sponge, but more finely powdered, a little bit of maybe oxide content. Used for electronics, electrochemical catalysts for electrolyzers, sensors. Ammoniated PGN salts are used as, again, catalyst precursors, but specifically for petrochemical applications. Some organometallics. I showed you that manufacturing area. Karstead catalyst, I don't know if anyone's familiar with that. That's a platinum-based catalyst used industrially for silicone cross-linking reactions. So taking two liquid silicone rubbers and making a solid silicone. And then supported catalysts for pharmaceutical applications, fuel cells, eye care, etc. Eye care, I have to mention the eye care discs. It's the closest thing we make to a finished product. We reduce platinum under the surface of these little plastic discs. If you can see that picture in the top right, I don't know if anybody has ever seen one of these or used one of these contact lens cleaning kits. You put your lenses in that little plastic thing and then it goes in a cleaning solution. That gray disc at the bottom is actually what we manufacture, and it's just a surface of platinum to catalyze the decomposition of hydrogen peroxide to facilitate cleaning of your lenses and also neutralize the peroxide so you don't burn your eyes. So I had to put that picture up. That's the closest thing we make to an actual finished good, I guess. So since we're talking about sustainability here, a couple of the products that we make, I saw somebody else talking a lot about PEM electrolyzers, so I'll just mention it briefly. My team was involved very recently in the scale up of an iridium black product that's used for this PEM electrolyzer technology. Platinum black is the other catalyst that's used at the cathode. And then fuel cells catalysts, again, here's a diagram of a proton exchange membrane fuel cell stack. So this is sort of the opposite of an electrolyzer. In an electrolyzer, you use electricity to make hydrogen. This one, you are generating electricity from hydrogen and oxygen. But platinum on carbon catalysts are used for the anode and the cathode, and we manufacture those products out of West Deptford. And one final note, I was thinking about this, it's just a random thought. We have I talked a lot about the global initiatives and how the company contributes to sustainability. Sustainability at a site level is something that we're trying to, tackle as well. And there's the one thing I deal a lot with process safety in my group, and trying to make sure that our processes are running safe. We understand the hazards, the critical operating parameters, and there's a concept in process safety called inherent safety. There's 4 pillars of that: eliminate, minimize, moderate, and simplify. So anywhere you can, if there's a hazard, if you can just eliminate the hazard by using a different chemical that's more safe, that's that's the way to go. You minimize the amount of a hazardous thing. You moderate how you use it in a more controlled fashion or a more dilute, a safer form, or you just simplify the process from an engineering perspective. So they're process safety concepts, but it's also, it kind of ties into sustainability, because PGM chemistry, you've heard me mention a lot of hazardous chemicals. PGM chemistry just requires the use of a lot of nasty things. So if we can't change the chemistry, then maybe we can approach it from this inherent safety standpoint, trying to use less of it, trying to use different reagents, trying to moderate the process in some way. And I believe that's it for me. So
Awesome.
yeah, that's what we do. We inspire science and we enhance life. So I hope that was enough, not too much time. I know it's the last talk of the day.
No, you're good. You're within time. All is well. Thank you so much for your talk. If everybody will join me in thanking Dr. Pawlikowski for his talk today. And now will be a time for questions. If anybody has any, feel free to submit them in the chat, raise your hand. If you want to ask anything anonymously, feel free to send them to me or Marta. But, oh, go ahead, Cooper.
Oh, I guess so. I can start off with a question. So I really found it interesting how like your talk was showing how Johnson and Matthey is promoting a lot of circularity within the platinum industry, and about the operations in the Eastern Seaboard where platinum from different cars and other products goes into smelters and then gets shipped to Johnson and Matthey for further processing and refining. Would you say in general that inside of like the US domestic market that the rate of recycled material uptake has been going up in comparison to the amount of platinum that we're getting from traditional places like South Africa, where it's coming from a primary ore recently?
Yes, very good question. So yes, I would say that our target, I think it's something like 70% of our PGMs as a company come from these recycled sources right now, and we're targeting to increase that to 75%, I think, over the next few years. At West Deptford specifically, we do get some mining concentrates. None of the materials we receive come from overseas. So there's actually North American PGM mines that's where we get our feeds. And then a lot of the big refiners in South Africa now working with Johnson Matthey, 100 years ago or almost 100 years ago, kind of partnered to establish this refining technology. So a lot of the mines in South Africa and Russia actually have their own refining capabilities there. So we focus more heavily on the recycling side.
Thank you.
Okay, I have a question of my own, and I also have an audience question. So the audience question is, where do you see the future of Johnson Matthey moving in terms of recycling materials? Do you ever see this company incorporating more metals than the ones discussed today?
Very good questions also. So there was, I caught a little bit of a previous talk. Specifically, there was some specific discussion about iridium supply related to fuel cells and electrolyzers. So iridium is scarce. If we're going to really make this technology work, we're going to be using a lot of iridium. So I think the next phase for Johnson Matthey has to be, we have to get involved in the recycling of products used in fuel cells and electrolyzer technology. So is there more value you can get out of that in terms of the other components, the membranes, whatever? I'm not sure, but that's a critical part to enable this hydrogen economy. Is you don't have an unlimited supply of iridium in the mines, so we need to ensure circularity with these new markets, I guess. As far as other metals, actually, we made an attempt recently. There was a lot of focus on battery materials for a while, but the company recently made a decision to divest those assets as well. So I think we were just a little too late in the game in some of those battery materials. There's challenges with those just because they're more abundant. So refining is expensive, but if the metals are valuable, then it makes sense. But it's a little more difficult with some of these cheaper base metals, I guess.
Awesome.
So for the time being, sticking with PGMs for the most part. But there are other metal catalysts used in the process technologies, for example, uses other cobalt, whatever, nickel catalysts. So but our bread and butter is PGMs.
Thank you. And so I have a question for you, mostly from a grad school perspective. But so many of us on this call are grad students, and some of us work in organometallics very similarly to what you did. What was for you the scale up process like to go from grad school working on like a benchtop to going to a factory and learning about all of that and how to do different things at larger scales?
Yeah, so that was a huge shock to the system for me, just getting into Johnson Matthey and realizing the scale that we operated at. So I remember in Karen's lab maybe doing a couple grams of a platinum precursor, doing milligram scale NMR reactions, and then all of a sudden we're doing 1,000 troy ounce batches of CPA. But once you get your head past that, I mean, the chemistry is the chemistry. There's a lot of process engineering that has to go in. You know, things behave a lot differently in the lab at small scale. There's a lot more consideration that you need to take to run it at large scale. And a lot of that is heavily engineering based, you know, heat transfer, mass transfer, that kind of thing. Really getting a handle on exotherms and gas generation and things like that. So you can get away with a lot more in the, you know, or with a Schlink line, just trying to synthesize a compound, and you know, you don't really have to consider what kind of off gases you're having, or you know, you have a reflux condenser, so everything's fine. But yeah, it's a lot more considerations from a safety perspective to ensure safe operations. I don't know if that answered your question. Or
Yeah, that was great. Thank you so much. Is there any more questions from?
I guess I have one more question. So we're talking about how catalytic converters were a large part of, I guess, like the platinum metal group feedstock. With the transition between internal combustion engines and electric vehicles, there's really not going to be much platinum put into catalytic converters anymore because catalytic converters won't be needed. Is I guess your company preparing for like any sort of supply chain disruptions in the next coming decade with that transition?
Yeah, so of course there's other teams that are heavily focused on this in the future, the 10-year plan, the 15-year plan, et cetera. I think you mentioned a decade. I think that's a little bit early. So even if the transition happens to these vehicles, it's still going to be a lengthy process to get all of the existing internal combustion engines and catalytic converters off of, you know, out of circulation. So we will still see recycling happening for a long time after the transition more to the battery vehicles and the fuel cell vehicles. But you know, so that'll keep platinum flowing, you know, through the recycling market for a number of years. And then we just have to make sure we capture, you know, the electrolyzers and the fuel cells are still using platinum catalysts. So again, it goes back to the point of making sure we're prepared to be able to process those materials to recover the value. So we have to adapt with the times, you know, and that's what we're trying to do.
Thank you.
So we probably have time. So we're close to the end, but we probably have time for one more question. If anybody has anything burning that they just would like to know or ask. So I have one more to, sorry.
You agree?
From the audience. So it reads, you mentioned working with engineers and other professionals. Can you talk a little bit about how working with them differs from your grad school experience and collaborating in that regard?
Sure. My biggest learning, I think, from starting to work with chemical engineers at my plant was they knew surprisingly not too much about chemistry. So I think the big collaborative effort when working with engineers on the floor is you really have to make them understand the chemistry. You know, the chemistry drives the hazards. The chemistry drives you have to understand the chemistry that you're doing before you can implement a safe process or troubleshoot or optimize. And the refinery in particular, it's such a fast-paced manufacturing environment. They just need to move metal constantly, and you don't have the time to solve every problem and think about every issue. So I also had to learn coming out of academia that I'm not going to have the answers, and at some point you just have to pick something and move on it, and just monitor and adjust on the fly. So it's kind of a learning from both ends, trying to make sure that they understand the chemistry and you understand when to give up and just try something and move on. So.
Awesome. Well, we are probably at about the end of time. So if everybody would join me one more time and thank Dr. Pawlikowski for his talk today, and I will turn it back over to Marta.